Good day, Math 30-1s. Today we look at 8.3, the lesson that involves the laws and rules of logarithms, which can be a little bit tricky just because the same idea behind exponents is implicit here, that log of 2 plus log of 3 does not equal log of 5. So somehow there isn't this straightforward logic that we add our inputs to get a new input. The laws of logarithms are on our formula sheet, and they are sort of listed below. But from exponents, we do know that there is a connection between adding and multiplying and subtraction, division. Like when we would say x squared times x to the 4, we are actually adding the powers because it's x squared and x to the 4, which does simply say there are 6 x's. You would typically just say 2 plus 4 is x to the 6. But this same sort of idea is implicit in logarithms, where we could say log of x plus log of y, and as long as they have the same base, we can say log of x times y. So the inputs come together as a product in the same input, in the same log. Same thing is possible for division, but starting with subtraction, log of x minus log of y is log of x divided by y. The last rule is a little bit strange, and it says if you have a power on your input, x to the power of m, this is not saying the whole thing is squared. It's not log base b of x and the whole thing is to the power of m. That's not what we're talking about. We're saying that little x has an m that could actually be brought down in front as a coefficient on the log base b of x. And without proving it, that is taken directly from that very, very top example, and is simply saying if you've got the same x as the other input, this formula comes out of that. So we'll get a couple examples below and see how this works. The first one says we've got log of 3 plus log of 2. This is very much the first one where we could put these together as a log of 3 times 2 or log of 6. I'm not asking you to evaluate at the moment. I'm simply asking you to use the formulas to combine the following expressions. For the second one, because we've got again the same base, log base 2, we can take this subtraction and write this as log base 2 of division of 15 over 3, which could be even more concise, log base 2 of 5. Nothing too crazy. Now, in the try examples below, what I've got is 3 separate things. You might question things slightly at this point, but if you write a single log and say there's a top and there's a bottom, we could ask what goes on the top, what goes on the bottom. Well, if there's a plus in front of the log of 7, the input goes on the top. Because there's a plus in front of the log of 2, the 2 goes on the top. Because there's a subtraction or a negative in front of the log of 5, that 5 is going to go onto the bottom, and we could write log of 14 over 5. Final answer. For the very last one, again, there's a positive, negative, positive. It's most easy to simply write a single log, a fraction in the input, and say what goes on the top, what goes on the bottom. Well, it's a positive log of 20, so 20 on top, subtracting a log of 10, so that 10 goes on the bottom. The positive log of 4, which means the 4 goes on the top, and this is an 80 divided by a 10, a log of 8. Alright, well, logarithms tend to ask or expect a lot of understanding of the rules and be able to work with them. So as we look at a potential backwards question, what I put together was some values like log base 3 of x is 5, log base 3 of y is 7, and log base 3 of z is 6. So an algebraic conceptual question, which means you can't really use your calculator for this. It's also log base 3, which makes it trickier depending on your operating system. But determine the value of log base 3 of x, y over z. Well, this isn't log base 3 of x, y over z. Yeah, this is 3 separate logs, 1 log. So why don't we separate, going backwards, surprise, surprise, separate this into a log base 3 of x plus a log base 3 of y, subtracting a log base 3 of z, which means we actually have these 3 expressions as values. Log base 3 of x is 5, log base 3 of y is 7, and a log base 3 of z is a 6. So there's a 12 minus a 6, which is 6. So a bit of a strange question, but it forces you to think a little bit backwards. So there's a little bit of practice just below, which asks us to use a few more of the rules. In the first one, log base 3 of 27 to the power of 5. How do we evaluate or determine the final result, the numerical value of this? Well, I'm not so great at saying 27 to the power of 5 in my head, but the good news is we don't have to know that. The third rule tells us that if we have a power on our input, we could shift that down in front as a coefficient. So let's shift that 5 down in front as a coefficient on the log base 3 of 27. This feels a little bit more appropriate because I can evaluate log base 3 of 27. You'll do your loop and say 3 to the what is 27? 3 to the 3. This is 3. We're actually being asked what is 5 times 3, which is 15. Again, 10 to the 40, not so good at that, but I can bring that 40 down in front and say what is 40 times a log of 10. Again, doing your loop, you could say 10 to the what is 10, 10 to the 1 is 10, and 40 comes out. So a few below to try. If you wanted to pause, try them, and then double check, you're more than welcome to. Otherwise, I will continue. Some of these are just simply evaluating without tricks, but the first one is asking 2 to the what is 48? Ooh, that is actually a little bit deceptive. If there was another way to write the 48, that would be kind of convenient. We can write this 48 as a 16, as a 2 to the power of, we can write that log base 2 to the 48 as log base 2 of, that is a, tricky. Well, why don't we put it together and call it a single log, 48 over 3. Well, this is simple. It's log base 2 of 16. What is log base 2 of 16? 2 to the what is 16? A 4. Sometimes logarithms can feel a little bit stressful until you see the strategy or the rule that can make it way more simple. Log base 2 of 3, that's not simple. Log base 2 of 48, not simple, but again, using that first rule made it a lot more simple. Again, 32 cubed. Why don't we bring that 3 down in front as a coefficient, which then we can evaluate log base 2 of 32. And you're getting so good at these base 2s that you could simply say 2 to the what is 32. You might need your calculator to say 2 to the 5, or you're getting that good already. 3 times 5 is another 15. Letter C, log base 3 of 18. Not a nice number. 3 cubed, 3 squared, nope. So maybe we'll have to put it together. Let's write this as a single log, log base 3 of. This is an addition, so let's multiply them together. 18 times 3 over 2. This becomes a 9 times 3. This is a log base 3 of 27. 3 to the what is 27? 3 to the 3. And for the very, very last one, the issue with log base 5 of 40, subtracting a 3 log base 5 of 2, is that 3 coefficient is in the way. We're actually allowed to put that coefficient back up as a power and say log base 5 of 40 minus log base 5 of 2 cubed. And I'm going to write that as an 8 because now we can actually put these back together and say log base 5 of 40 divided by 8, which is a 5. And 5 to the what is 5? 5 to the 1. And for a very, very last one, another conceptual question which makes you think a little bit deeply. It gives us some information and asks us to determine a value of something kind of strange. Log base 3 of 27f squared. What is the value of that? Well, the only information we have is what log base 3 of f is. So maybe we're being asked to pull this apart and use that first log base 3 of f value. So I'm going to take this log base 3 of 27f squared, and the squared is only on the f, and I'm going to pull those two apart and start to see if we can create a log base 3 of f to appear. Log base 3 of f squared. Now this is getting kind of convenient because we can pull that 2 down in front and say 2 log base 3 of f. Log base 3 of 27 is simply hanging out. And I can evaluate log base 3 of 27 as 3 cubed is 27, so a 3. And I can say 2 times log base 3 of f is k, 2k. This is the algebraic value of log base 3 of 27f squared. Again, a very conceptual question which asks you to think a little bit more deeply about the rules without being able to use a calculator. A couple last ones, one involving some simplifying and one about pH and acidity. And so the top question asks us to simplify expressions and to state any restrictions if we reduce anything. So what we have is a subtraction of 2 log base 7s. Let's just see what happens if we do put these together to make it look a little bit more simple. Because this is a subtraction, we've got our 2x minus 2 on the top and our x squared plus 2x minus 3. Is this as simple as we could go? To which everyone watching says, no, there's more we could do. We could factor the top and factor the bottom and hope that there is something that can simplify, something that could cancel. If we factor the top, an x minus 1 factor shows up. If we factor the bottom, hope is that an x minus 1 factor shows up, and it does. Cheers from the crowd. X minus 1s do show up, and what we're left with is a log base 7 of 2 on the top and an x plus 3 on the bottom. It's important to remember that you're not actually allowed to have a negative input, and you're not allowed to have, in this case, a 1, because we actually got rid of part of the expression that was originally there. It seems like 1 is allowed, even though in its original form 1 is not. So 1 is not allowed, but even though it's not written, you're still not allowed to have negative inputs. So this simply shows the restriction that is no longer visible in the question. All right, on to pH and acidity. So pH is a topic in chemistry that is attached to how acidic or basic things are in the real world. And the pH scale has acids ranging from pH values of 0 to 7 and bases ranging from 7 to 14, where 7 is neutral. The stronger the acid or the base, the further it is from 7. So the formula for pH, px is equal to is negative log of x, where x is the concentration of hydrogen ions that is in some sort of substance. So questions can start off simple and then might ask about comparing like we did with the earthquakes. So the first question says the hydrogen ion concentration is 0.01 units are moles per liter. Is it an acid or a base? So if we plug in 0.01 moles per liter, we have a negative log of 0.01, And when you type in your negative log of 0.01, you end up with negative of -2, or a 2.0. So because this is a 2.0, it falls in the acid side of things. So because it's between 0 to 7, this is an acid. Well, last question on the page says, an apple has a hydrogen ion concentration that is 5 times the amount as a pear. If a pear has a pH of 3.8, then what is the pH of an apple? Fairly complex question. But it says that a pear has a pH of 3.8. Let's just organize this. It says something about an apple has a hydrogen ion concentration 5 times that amount as a pear. Then we're being asked about an apple. What is the pH? So what we're going to need to do is take this pear, determine its hydrogen ion concentration, times it by 5, get the hydrogen ion concentration for the apple, and then determine its pH using the formula. Let's just do this under each level to keep this organized. So we have a formula which says negative log, I'm going to write a little base 10 in there, of our hydrogen ion concentration. What we're needing right now is our hydrogen ion concentration, X, from our px. So if we rearrange this formula using the loop, we might have to get rid of that negative first. So I might be a little bit cautious and rewrite this by saying the pH, and let's write this for its simplicity as an actual pH. So we move the negative over to the other side. Negative pH is log base 10 of X. Now if you're in chemistry, you've done chemistry, when I say 10 to the negative pH is your hydrogen ion concentration, you've seen that before. So we're going to do 10 to the negative pH to get our hydrogen ion concentration. So for a pear, we have X is 10 to the negative 3.8, which is going to be a decimal, a very, very small decimal, and in scientific notation it shows up as about 1.58, 4, 9, 3, and so on. Let's multiply this by 5 and keep the values in here. It's about a 7.92, and so on, times 10 to the negative 4. And then we're being asked to take this value, which I'll shorten it to say it's about 7.92 times 10 to the negative 4. And we're going to take this and we're going to figure out the pH. So the pH is negative log of this 7.29 times 10 to the negative 4 with all those decimals in it. So we go back to our calculator and we can type in negative log of this previous answer, and it should tell us 3.1. So the pH is about a 3.1. Because the concentration of hydrogen ions was more, we ended up having a more acidic fruit. So often your understanding of logarithms isn't limited to here's a number, plug it into a formula. Often it expects a little bit of a deeper understanding to compare, to deal with the rules, to deal with the laws. Thus ending our third lesson in logarithms.